Hello everyone, today we are going to solve one of the finest and toughest questions on circles, geometry and angle properties of circles especially that came up in DSAT papers previously, and we're going to look effective approaches to solve out these finest questions on especially on circles. So we're going to start with this first question, and before I walk you over with this question, I would really like to discuss some of the critical angle properties of circles which got tested, especially in this question. So I'm going to start with those properties first. Yes, I can see bunch of similar triangles over here, but I'm not going to apply similar triangles or trigonometric ratios approach in these type of questions because some students find it really difficult to find out the corresponding lengths, which angle corresponds to which length in a given scenario for two similar triangles. Okay, so what I'm going to do, I'm going to start with some angle properties of circles that are being tested in this question. For example, I did discuss those specific angle properties of circles in my previous formula sheet, and in case some of you might have missed it, we can just have a quick look at those angle properties of circles. For example, the first one and the second one, specifically these two specific properties were tested in this question. So what's the first property that we're going to look at before we actually start solving this question? So for example, if you have a circle like this, and then you have a chord somewhere on the circle, let's say like this, and let's say you have a line which is coming from the center. So for example, there is a line which is coming from the center, which passes through the center and is perpendicular to your chord. That's the first property. A line coming from the center which is perpendicular to your chord. In all these situations, that line which is coming from the center will always bisect your chord. So it will actually hit your chord right at the center. It will cut your chord into exactly two equal halves. That's the first property. And the second one is, for example, let's say again you have a circle like this. And let's say this time you have got two different chords in this circle. For example, one of them looks like this, and the other one is basically intersecting this chord at some point, for example, over here. So if you look at the black chord first, for example, if I name this line segment as A and the rest of the portion as B, and now let's have a look at the red chord as well. For example, if I name this C and the remaining portion of the red chord as D, the property says that the product of the segments of two chords, for example, A times B, for the first chord, the product of the segments of the first chord should be equal to the product of the segments of the second chords. A times B should be equal to C times D. That is what the property says. So we're going to look specifically at these two properties of angle properties of circles to just solve out this question. For example, what do we see over here? In the figure shown, U, V, X, and Z lie on the circle, and there's some specific information to given to you about Vx and Vz. Now segment XZ is the diameter of the circle. So now when the question says that this is my diameter of the circle, so obviously diameter always passes from the center. So this is a line coming from the center, passing through the center of the circle. And if you see, it's actually bisecting your chord VU at an angle of 90 degrees. It's hitting your chord VU at an angle of 90 degrees, which automatically means that this length should be equal to this length as per this first property that I just discussed with you guys. Now, what else is given to us? We know the diameter's length is 150, but very important information over here is that we know what is Vy actually equal to. That's under root 296. So I can name this as under root 296. So let's say this is under root 96, and obviously this should also be under root 296 as per the first property that I just discussed. This should also be under root 296. Now, I know the entire length of xz, but I don't know the breakup of xz into zy and yx. So for example, I can name this smaller portion yx as x centimeters. So automatically the bigger portion zy would become 150 minus x, because the total length that is given to you for this entire diameter is actually 150 centimeters. So can I apply this second property of two intersecting chords? Yes, I can. For example, if I have a look at this first chord, zx is broken into two regions, into two segments, zy and yx. One of them is 150 minus x and the rest of the portion is x centimeters. So I can create an equation over here, a times b, or 150 minus x times x should be equivalent to, now this is actually intersecting your chord VU, and we know the two segment lengths of VU as well. That's under root 296, that's under root 296 again, so that should be equal to C times D. Under root 296 times under root 296, I can just create an equation like this, under root 296 times under root 296. So that's my equation that I'm looking to solve for the value of variable x. So if I simplify this one, I would be getting 150x minus x squared, or minus x squared plus 150x is equal to root 296 times root 296 should be obviously 296. So I've created a quadratic equation over here, and I can solve this quadratic equation on my scientific calculator. So what I'm doing, I'm just typing this entire quadratic equation on my scientific calculator, starting with the coefficient of x squared, that's -1, and then I've got a positive 150, and then I've got 296, that would obviously minus 296 once you subtract 296 on both sides. So I'm getting my value of x. I'm getting two values of x basically. One of them is coming out as 2, and the other one of them is coming out as 148. So these are the two values of x that I'm getting. So I can say, because that literally looks smaller to me, yx, so I can name this x as 2. I am not looking to name this x as 148. I know that the figure is not drawn to scale. It could be 2, it could be 148 as well, but if this is 148, automatically this would come out as 150 minus 148 as 2 centimeters, and zy would obviously become smaller than yx. But again, I am looking at this statement that the figure is not drawn to scale, but if you look at this information at the top, it says that Vx, which is basically the line segment of the smaller triangle at which you have the length x, is basically less than Vz, and Vz is basically the line segment of the bigger triangle on which you have 150 minus x. So this is bigger. Vz is definitely bigger, therefore zy should also be bigger and yx should be smaller. So I'm going to take x as 2 over here. So this is 2, and automatically this would become 150 minus 2 as 148. And if you look, I just have to find out the ratio of these two lines. What do I have to do? Xy divided by yz. I know what is xy, that's 2, and yz is basically 148. So that's basically the ratio of these two numbers. K represents the ratio of these two numbers, 2 divided by 148. And again, you can simply type this in your calculator as well. You will get your answer as 1/74. That should be the right value of your constant K over here. So I basically applied the concept of angle properties of circles. Coincidentally, the first two properties that I discussed in my formula sheet were actually tested over here. I never used the bunch of similar triangles to solve out corresponding length ratios because I really believe that students sometimes find it really confusing. Okay, now moving on to the next question. Okay, so here is another question for you. The perimeter of an equilateral triangle is 72 centimeters. So obviously each side length of this equilateral triangle should be equivalent to 72 divided by 324, because equilateral triangle has all three side lengths equal to each other. Now it says that the three vertices of the triangle lie on a circle, which means that this equilateral triangle is basically inscribed in a circle. For example, let's say you have a circle like this, and then this equilateral triangle is basically inscribed in a circle like this. I did discuss the inscribed and circumscribed formulas. For example, if I have a look over here, I did discuss some of the finest formulas because I really noticed DSAT using these concepts frequently. So I converted some theorems and I shared those theorems with my students. For example, if you look over here, when an equilateral triangle is inscribed in a circle, what's the formula? The side length of that equilateral triangle is always equivalent to the radius of the circle times √3. Okay, do we know the side length of this equilateral triangle? Yes, each side length is of 24 centimeters. So I can use this formula. S is equals to r times under √3. So I know what is S, that's 24, and r is something that I'm looking to figure out because I need to quote the radius of the circle in the form of w under √3. All I'm doing is again typing everything on my scientific calculator. So 24 divided by under √3, the calculator would automatically rationalize the fraction for me. So I'm getting my answer for radius as 8 under root 3. And if you notice, you have to find out the value of w, and w is basically the number behind root 3, and the number behind root 3 is basically 8. So that's the value of w. That's the basic formula. That's, by the way, one of the hardest questions on equilateral triangles and angle properties of circles that came up in the paper. Now, I literally solved this question using this simple theorem, simple formula, S is equals to R under root 3 in literally under 10 seconds. If you know this formula, you would be able to solve this question in literally under 10 to 5 seconds. Now, that's the value of radius, but I believe that some students are very good in memorizing all the theorems, but some students are not very good in memorizing theorems. They're good in generalizing a given situation. They're good in developing their theorems in a given situation. So for example, if you don't know this formula, what you're going to do, obviously you're going to draw this entire shape. So for example, you have a circle over here, and then inside this circle you have an equilateral triangle. Sorry for the rough sketch. So basically this is my equilateral triangle like this, and I know each side length of this equilateral triangle, that's given to me as 24, 24, and 24. Okay, so I need to find out the radius of the circle. So for example, let's say this is my center of the circle, then this length from here till here, obviously that should be my radius, right? And this length from here till here, that should also be my radius, and this length from here till the circumference of the circle, that should also be my radius. Now, can I know this angle? Yes, I can calculate this angle because this entire circular angle would be equal to 360 degrees. So you're going to divide 360 by 3 to find out the angle of this particular arc. So this should come out as 120 degrees. I know this angle. This is 120 degrees. So what if I drop a perpendicular from here? What if I drop a perpendicular from here? So if I drop a perpendicular from here, obviously it is going to bisect this side length of 24. Since this is a perpendicular, it's again one of the finest properties of triangle. If you're dropping a perpendicular from in between of two equal sides, this R and R are two equal lengths. If you're dropping a perpendicular from in between two equal sides, that perpendicular is always going to bisect your base. So this 24 is going to split itself into exactly two halves. This would be 12. And so as the other one as well, but I'm looking to operate over this triangle. Now, what would this angle be? This angle is going to bisect itself as well. That's one of the properties of triangles, right? This should be 60 degrees, and automatically this angle would come out as 30 degrees. Now, can you see a 30, 60, 90 degree triangle? We have created a 30, 60, 90 degree triangle inside a circle. And if you're good with ratios of triangles, for example, if you know what is opposite to 30 and you want to figure out what should be opposite to 60 degrees, just multiply the side length of 30 degrees by root 3. If you want to figure out, if you know what is opposite to 30 degrees and you want to calculate what should be opposite to 90 degrees, in that case, just double the side length opposite to 30 degrees. And the third ratio, that is core part of the course, is basically while moving from 45 degrees to 90 degrees, you know what is opposite to 45 degrees, and for some reason you know what should be your hypotenuse or what should be opposite to 90 degrees, you're going to multiply 45 degree side by under root 2. In this case, if you look very carefully, I really know what is opposite to my 60 degree side. That's 12 centimeters over here. So obviously, the side opposite to 30 degree would be 12 divided by root 3, because I'm actually traveling backwards. I'm not traveling from 30 to 60. Instead, I'm traveling from 60 degrees to 30 degrees, because I know what is opposite to 60 degrees. I need to calculate what should be opposite to 30 degrees. So that means I'm traveling backwards. I'm not going to multiply by root 3 this time. Instead, I'm going to divide by root 3 this time. So now I know this side should be equivalent to 12 divided by under root 3. So now you know what is opposite to 30 degrees. That's 12 over root 3. So obviously opposite to 90 degrees would be what? If you know what is opposite to 30 and you want to calculate what should be opposite to 90 degrees, just double that number. 12 over root 3 times 2. That should give you this side as 24 over root 3. So my radius of the circle, or this green length, is coming out as r is equals to 24 over under root 3. And again, if you want to simplify this fraction, you can always do it using a scientific calculator. I'm just typing 24 divided by under root 3 in my scientific calculator. Automatically the calculators are good enough to rationalize your denominator for you, and it's coming out as 8 under root 3. So my radius is coming out as 8 under root 3 again. And again, if you see the coefficient of root 3, or you can say the number behind the number root 3, that is supposed to be your value of w. So w over here from both the methods is coming out as equivalent to the number 8. So I show the formula method, and I then show the generalization method, where you draw the diagram and you try to see what theorems are being applied in a given diagram. Now moving on to this question, since we just discussed ratios of triangles, that's another question on angle properties of circles and ratios of the triangle. So for example, in this question, the examiner really says in the figure below, O is the center of the circle. So this is my center of the circle, and RT is tangent to the circle at X. So obviously this angle has to be 90 degrees, because this is another property, angle property of circle. The tangent is always perpendicular to your radius / diameter of the circle. And the line YZ is parallel to RT, so this angle has to be 90 degrees. Again, the two corresponding angles that you can see. And if triangle RST is equilateral, that's the biggest information that the examiner has given to me. So this should be equivalent to 60 degrees, right? This should be equivalent to 60 degrees. And over here, this entire angle S at the bottom should be equal to 60 degrees again. But half of it would be 30 degrees. So I can actually see a 30, 60, 90 degree triangle XST, which clearly means that the examiner is trying to test my understanding of ratios of triangles. I can see another 30, 60, 90 degree triangle. For example, if you see the smaller triangle, this one of them has a vertex of O and Z, and then this vertex right over here, the center point of YZ. This is 30, this is 90, so automatically this angle should also be equal to 60 degrees. Now I can see 30, 60, 90 degree triangle. Obviously, these two triangles have to be similar to each other. But if you look very carefully, you don't have to find out the exact lengths of RT and YZ. Instead, you have to find out the ratio of these two lengths. I can suppose any number. For example, I'm always comfortable to start with the side length opposite to 30 degrees. So I'm taking this 30 degree side opposite to 30 degree side as 5. So automatically, the side opposite to 60 degrees would come out as 5 under root 3, which means if this is 5 under root 3, then I've got a congruent triangle on the other side as well. This should also be 5 under root 3 as well. So this is also 5 under root 3. And if this is 5 under root 3 and this is 5 under root 3 altogether, that would give you a 10 under root 3, right? So I know the base length. I know my denominator basically. I know my denominator YZ. That's coming out as 10 under root 3, 5 under root 3 plus 5 under root 3. That's 10 under root 3 right over here. And if you might have noticed over here, when you said that the side opposite to 30 degrees is 5, then this side, which is basically opposite to 90 degrees, that should be double. OZ should be double of 5, because you're traveling from 30 to 90. And this is essentially a very important side length, because if you see very carefully, OZ is representing your radius of the circle. Radius is, by the way, the most important dimension in a given circle. So that should be equal to 10. And if you're saying that this is 10, then this entire side XS, if you look very carefully, side XS, that's the side I'm talking about. That is basically my diameter of the circle, right? That should be 20. That should be 20, double of my radius. That should be 20. Now, if you look at this bigger triangle, the 30, 60, 90 degree triangle, opposite to 60, that's 20 over here. Then that means opposite to 30 degree would be 20 divided by under root 3, right? 20 divided by under root 3. The side length opposite to this 30 degree at the bottom. And if this is 20 over under root 3, this should also be 20 over root 3. A genuine question on ratios of the triangles, which means my RT side, that's something that I need to calculate. 20 over root 3 plus 20 over root 3 should give you a 40 over under root 3. 40 divided by under root 3. Now, I'm literally again typing everything on my handsome scientific calculator. 40 divided by under root 3 divided by divided by 10 under root 3. The calculators will simplify it for me. You can use a Desmos as well if you want to. You can use anything if you want to, any device that you have that you're using, basically the scientific calculator that you're using in your DSAT paper. I'm just typed everything on my scientific calculator. I'm getting my answer in the most simplified form as 4/3 over here. So that's what a genuine question on ratios of the triangles with some concepts from similar figures as well. So we have done another hard question that came up in DSAT papers, specifically on circles, equilateral triangle, and ratios of the triangle. Okay. Let's have a look at this question. In the figure below, the circle has an area of 16 pi. So what can we calculate from this information? If 16 pi is the area, 16 pi needs to be equated with pi r square, because that's how the formula for area of the circle works. Area is always equal to pi r square. Pi and pi are cancelling each other. Square root the number 16, you will get your radius as 4. And if your radius is 4, then automatically this diameter from top to bottom, this will be your diameter of the circle. Obviously, that should come out as 8. But this is not just the diameter of the circle. This is also the height of your equilateral triangle. The height of your equilateral triangle, or the altitude of your equilateral triangle, is coming out as 8. Now, I did notice that your examiner is giving a lot of questions on specifically on equilateral triangles. I also created some formulas on equilateral triangles as well. And we're going to look at those formulas right over here, where I discussed some concepts from triangles. Okay. Over here, can you see I discussed this formula? Height of an equilateral triangle is always equivalent to under root 3 over 2 times s. So I know what is my height, that's 8. So 8 is equals to under root 3 s over 2. So if you divide both of the sides by 2 over under root 3, so that would come out as 16 divided by under root 3. My side length of the equilateral triangle is coming out as 16 divided by under root 3, right? So this bottom side length, and in fact all the 3 side lengths, are actually equal to 16 divided by under root 3. And at the same time, I also discussed one of the finest formulas of area of equilateral triangle. By the way, you can use half AB sine C as well, because all the angles are equal to 60 degrees. But again, there's one formula right in front of you. Under root 3 over s square, specifically used for the area of equilateral triangle. So you can just put the side length in this formula, under root 3 over 4. I'm just basically using simple formulas that I've been using a lot of times in these DSAT questions. 60 divided by under root 3 square. And then very careful, I'm going to type everything on my scientific calculator. Make sure that you're not doing anything manually, because you need to, obviously the first thing is that you need to avoid all the silly errors that you might can make in a given paper. And at the same time, you have to save your brain for all those harder questions in a given module. So for example, under root 3 over 4 divided by 16 divided by under root 3. Everything being typed on my scientific calculator as it is. Now once I simplify this, my calculator is giving me 64 under root 3 over 3. That's my answer, option C, right over here. So another question on circles and equilateral triangles is specifically, another very finest property of congruent triangles created through circles and tangents. For example, in this question, it says that there is a circle. Let's say this is my circle. I will try to create as accurate circle as possible. So this has a center at G, and points M and N lie on the circle. So let's say this is point M, and let's say this is point N right over here, and line segments MH and NH are tangent to the circles at the points M and N. So these are line segments. For example, the first tangent looks somewhat like this, and the second tangent looks somewhat like this. And these are basically intersecting at the point H. MH and NH are basically the tangents to the circle. Remember, I discussed this property where two congruent triangles are created in angle properties of circles. We can have a quick look at that property. For example, angle properties of circles. Property number 5, you will be able to create two congruent triangles, one at the top and one at the bottom, when these two tangents are meeting on the outside of the circles. For example, The wisest approach would be to draw the radius, because radii are always perpendicular to your tangent. So this should be 90 degrees, this should be 90 degrees. And whenever you're done drawing the radius, always create a center line, so that you can see that you would be able to create two congruent triangles. This triangle at the top would be completely identical with this triangle at the bottom. That is what the entire property says. Now what is given to you? If the radius of the circle is 150, that's 150 and that's 150 as well. Now moving on, and the perimeter of quadrilateral GHMN. What is GHMN? For example, this is G, and basically this is M, and this is H, and this is N. You can see a kite being created called as a quadrilateral over here, but it says that the perimeter of this entire quadrilateral is 3500 centimeters. I'm done with 150 and 150. Altogether, I'm done with a total length of 300 millimeters. So 3500 minus 300 millimeters, that would give you a remaining total of 3200 millimeters. And I need to divide this 3200 into two equal halves, because both of them should be equal in length. That is what congruency is all about, having identical lengths and identical angles. When I said MGH and GNH are two congruent triangles, that means two identical triangles. So if you're left with 3200 millimeters, it means that number 3200 is going to divide itself into exactly two halves. This would be 1600 over here, and this would be 1600 over here as well. Now what else do we know? We need to calculate the distance in millimeters between point G and H. This is point G right over here, and this is point H right over here. I need to calculate the length of this dotted line, and I'm dealing with a right triangle where I'm supposed to find out my hypotenuse. I can simply use Pythagoras theorem. For example, under root 1600 square plus 150 square. I've just typed it again on my scientific calculator. My calculator is giving me an answer as 1607.01, correct to the nearest whole number as 1607 as my answer, option C. So this was another question on angle properties of circles. Okay, let's have a look at this question. This is one very good question. I really like this question. It was kind of confusing with how the question was initially stated. For the given circle, let's have a closer look. The measure of arc ABC. Now what does ABC represents? Be very careful in how you interpret your arcs. A comes first, then B, and then C at the very end. So ABC, you cannot move like this. This would be ACB instead. You have to move like this. A should come first, and then B should come, and then eventually C should be your final point. So this is basically ABC. Can I draw this arc ABC? This red arc that starts from A, hits B, and then ends at C. That is your arc ABC. Now, for example, let's say this is my center of the circle. Then what is the arc that is created over here? What is this arc that is created over here? Draw a radius, and you would be able to figure out this arc. This red arc has an angle equivalent to 130 plus 7x. So I'm going to put 130 plus 7x over here. Now let's move on. Arc ACB, A, then C, and then B. Now this is, I think, the minor arc ACB, starting from A, then hitting point C, and then ending at B. This is your green arc ACB. Just draw the radius, one at B and one at A, just to enclose this sector, just to enclose this into a sector. Now if you see this angle from here till here, this angle over here is given to you as 90 minus 3x. I'm going to write it down over here. 90 minus 3x degrees. Okay, now what else is given to us? This angle 35 right at the circumference is given to us. Now, for example, can you have a closer look at this chord? For example, chord CB. Did I not discuss this very good property of angle properties of circles, where I told you guys that the angle at the center is always twice of the angle at the circumference? This one, angle properties of circles, property number 6. If this is x, then this should be 2x. If this is 100, then this should be 200. If this is 40, then this should be 80. Now, if you look over here, if you have a close look at this blue arc is creating one angle this blue chord basically, this blue chord is creating one angle at the circumference, that's 35 degrees. And at the same time, this blue chord is again creating one angle at the center. For example, this angle over here, this angle, this should be double of the number 35. This should be equal to 70 degrees. Double of 35, that should be 70 degrees. Angle at the center is always twice of the angle at the circumference, subtended from a common chord. Now, can you look at this green arc? Can you have a closer look at this green arc? This green arc is altogether equivalent to 90 minus 3x. Now, what if I subtract 90 minus 3x? What if I do 90 minus 3x? Minus 70. What should be this angle? What should be 90 minus 3x minus 70? I think this angle over here would be equivalent to 90. This black arc would be representing this measure, 90 minus 3x, and I've just subtracted 70 from it. 90 minus 3x minus 70 is the measure of this black arc. And the remaining portion of this black arc is basically your red arc, which is 130 plus 7x as already given in the question. 130 plus 7x. Don't you guys think, don't you guys notice that the sum of this black arc and this red arc, that's one complete cycle, that's one complete circle, that's one complete rotation. That should be equivalent to 360 degrees. So that's my equation over here. And I'm going to simplify this equation. Minus 3x plus 7x, that's 4x. And then everything on my scientific calculator again. So 90 minus 70, and then I see a positive 130. That's 150. Subtracting 150 on both sides. So 360 minus 150. I'm getting my right hand side equivalent to 210 degrees. And once you divide 210 by 4, so that should be 52.5 for the value of x. So very good question again on one of the most critical properties of angle properties of circles basically. Okay, let's have a look at one more question. Oh, I love equation of the circles, and I did shared this formula with a lot of my students. For example, if you have a general equation of the circle, let's say that looks like this: x square plus y square plus 10x minus 12y minus 13 equals to 0. That's your general equation of the circle. What is the general equation of the circle? Where the coefficient of x square and y square is always positive 1 and everything is on the same side equated with 0. So whenever you're looking to find out the center coordinate, by the way, the center coordinate of any circle are always called as h, k. So if you want to find out the value of h and if you want to find out the value of k, what are you supposed to do? Just divide the coefficient of term x by minus 2. So my coefficient of term x, that's 10. So 10 divided by minus 2, that should be minus 5. And just divide your coefficient of y by minus 2 again. So what is minus 12 divided by minus 2? You will get the value of k, constant k. So minus 12 divided by minus 2 is always positive 6. So this is h, k. And what's the specific formula for radius of the circle from any general equation of the circle is always equivalent to h square plus k square minus the constant that you see at the very end. That's the formula. And h and k, by the way, represents your center coordinates of the circles. For example, in this case, if you want to find out the radius value for the circle, you're going to do negative 5 square, that's 25. You're going to do 6 square, that's always 36. And then you're going to subtract the value of constant, which is basically negative 13 over here, minus 13. And you're going to type everything on your scientific calculator. And calculator will automatically simplify the radius for you. For example, in this question, we know what is h, we know what is k, and we want to figure out the value of this constant at the very end. So for example, and we also know the radius of the circle. So for example, if I try to use this formula, because I know the value of my radius, that's equivalent to 12 is equals to under root, and I know the value of constant h and k. 3 square, that's 9, and minus 7 square is always 49, minus the constant that you see over here, that's your c over here, minus c. So squaring on both sides will give you 144 over here, And then 9 plus 49 is 58 any day, minus C. And once you simplify this for your constant C, you will get what? 58 minus 144. That's coming out as negative 86. Negative 86, that's the value of your constant C. So that is how we were supposed to solve this question. 3 square, 9 minus 7 square, 49 minus the constant that you see over here. And the radius was always given to us as 12. So 12 square basically became 144 once I took square on both sides to get rid of this square root. Basically, I eventually solved a simple radical equation to figure out my value of the constant at the very end. Now, let's have a look at this question. Oh, I loved this question. I love this question. For example, before we actually move on to this question, I'm not sure if a lot of people know this very specific property of right triangles, because I normally do not share frequent theorems with my students, but when I notice a particular pattern in all those DSAT questions, I create formulas for those questions, and then I share those formulas with my students. Because once there is a particular pattern, DSAT is going to repeat that particular question for some years, for the next, let's say, 8 to 10 attempts. And if you know these specific theorems, there will be scenarios when, let's say, you're solving question number 22, module number 2, and you're expecting that question to be a very hard one. And for example, you know the theorem, you know the basic formula, you might be able to solve this question in literally under 5 seconds. For example, before we actually move on to this question, can I share one very important theorem with you guys? For example, let's say if I have a right triangle. What is a right triangle? Where Pythagoras theorem satisfied perpendicular square plus base square equals to hypotenuse square, or a square plus b square equals to c square. For example, let's say this is my 90-degree angle, and let's say this is my one of the legs, and this is my second leg, and let's say this is my hypotenuse. Let's name this as C. That's how the names are designed. The names were designed initially, A, B, and C respectively. So for example, if you drop an altitude from your hypotenuse like this, let's say this is my altitude of this right triangle, it's obviously going to cut your base into two lengths. For example, let's say this is P, and let's say this is Q. So what are some specific theorems? There's one theorem known as altitude segment theorem. What is that theorem? Altitude segment theorem. What is altitude segment theorem is all about? Altitude segment theorem says that height, this is, let's say, height of your height of your right triangle, h represented by h. It says that the height square or the altitude square is always equivalent to the product of the segments that you have actually created on your hypotenuse, because the altitude gets dropped on your hypotenuse. It's always equal to h square is equals to p times q. Some people like to call it geometric mean formula as well. And then there is leg theorems as well. Leg theorems. So what are leg theorems? There are two specific leg theorems. And what are leg theorems? Let's just discuss leg theorems as well. We know that one of the legs of this right triangle is basically a centimeter. So what is leg theorem? It says that a square, or the square of one of the legs, is equivalent to, you're going to take the adjacent segment, or the adjacent line, or the line next to this particular leg A. So what is the line next to this leg A over here on your hypotenuse? That's P basically, that's P. So you're going to take this P and you're going to multiply this P by a hypotenuse. So that's the formula. A square is equals to PC. Now, if you're taking this leg, you're going to use this particular segment, not this segment Q. But if you're taking this leg B, you're going to create again the similar formula, but now this time you're going to use Q instead of P. Which one of them is near? You're going to use that thing. For example, A is basically nearer to P, so you're going to use P, and you're going to multiply P by the hypotenuse. And for example, if you want to create formula for the second leg, that's B, you're going to use Q instead this time, because that's nearer to B than P is. So Q is actually narrow. So you're going to multiply Q by C. B square is equals to Q by C this time. This is called altitude segment theorem and leg theorems. For example, if you want to practice this question, for example, let's say I have this right triangle over here. Can you see this right triangle? And I need to find out the length of this line segment BC right at the bottom. So can you guys see that this is not known to me, but this is one of the legs of this triangle. X is one leg represented by BC, and BA is another leg of this triangle, and AC on whole actually represents your hypotenuse, because that's right in front of opposite to 90 degrees. That's your AC. So there's an altitude drawn at the base or the hypotenuse of this right triangle. So how can I figure out the value of this x? For example, I'm taking this x as x square is equals to, now x is nearer to which of these two segments? 16 or 9? That's actually near to 16. So I'm going to type 16 times the entire hypotenuse. My hypotenuse is basically 16 plus 9, 25. So I'm going to do 16 times 25, right? Now I'm going to simplify this using my calculator again. 16 times 25 square root. Square root of 16 is 4, and square root of 25 is always 5. So 4 times 5. That's 20. Done and dusted. The value of x is equivalent to 20 centimeters or 20 meters. For example, because I saw frequent questions on right triangles where the examiner dropped the altitude from the top at your hypotenuse. So I really feel that these formulas are really helpful. For example, you can use multiple approaches to solve this question out. You can use trigonometric ratios. You can use trigonometric inverses as well. You can use the concept of similar figures as well, and you can use the concept of area as well to find out the value of NQ over here. But for example, if I can see a right triangle with one of the legs as 3 and the other legs as 4, through Pythagoras theorem, that's the basic formula, you should be good enough to apply Pythagoras theorem in any given right triangle. So that should come out as 5. Under root 3 square plus 4 square is always equal to 5 square, right? Now what else can I do? For example, if I select this leg, 3 square is equals to, I don't know what is this MQ. So MQ times 5. So 3 square, 9. 9 divided by 5, that's MQ coming out as 1.8. So if this is 1.8, then what is 5 minus 1.8? That should be 3.2 right over here, right? So I know the segments in which my hypotenuse is divided, 1.8 and 3.2. What I can do literally, this is my altitude square, or NQ square, is always equivalent to the product of these two segments at your hypotenuse, 1.8 times 3.2. And again, literally I'm typing everything on my scientific calculator. So what I'm going to do, 1.8 times 3.2, and then square root of that number, square root answer. I'm getting my value of NQ as 2.4. NQ is coming out as 2.4 right over here. But I can use multiple approaches to solve this question. For example, let's say forget all the labelings done in red. For example, when the question started, you know that this was 3, this was 4, the two legs were given to as 3 and 4, and this was your hypotenuse, that's 5. So what if I try to find out the area of this triangle? One possible method of calculating the area of this triangle would be taking MP as your base, that's 5, multiplied by automatically anything perpendicular to MP would be your height. That should be your height. NQ would be height. So base times height divided by 2. That's how you calculate the area of the triangle. And you can again repeat the same process for this particular triangle, for this entire triangle, using your legs, because 3 and 4 are your legs of the triangle, or base or perpendicular of a triangle. What is the area? What is the general area formula? General area of the triangle, base times height divided by 2. So if you take this as your base, then automatically NP would be your height. So 3 times 4 divided by 2 again. So 2 and 2 cancels out. 3 times 4, that's 12. 12 over 5, that's 2.4 any day of your life. 12 divided by 5, that's 2.4, right? So I've used altitude segment theorem and leg theorem to good effect in many questions of DSAT. For example, if I have a look at this question eventually. Now, this is a circle over here. And the examiner says that BD is the diameter of the circle, but it's also the altitude of my right triangle. What else is given to me? AD, one of the segments at my hypotenuse, that's 27, and the other segment at my hypotenuse, another segment CD, is given to you as 12. And we really have to find out the height of this right triangle, or the altitude of this right triangle. So I can create again another equation. BD square should be equivalent to 27 times 12. And your final answer for BD, I'm basically about to solve one of the most hardest questions of DSAT in literally under 10 seconds. Basically, all you have to do in your calculator, 27 times 12 square root, that's coming out as 18. So that's how you're going to apply angle properties of circles. And I did mention all those properties, all those helpful properties in my detailed formula sheet that covers the entire course. You have everything, you name it, you have got it, from the chapter of algebra and advanced maths and geometry and trigonometry, and finally problem solving and data analysis. Everything, every single thing is being discussed in my comprehensive DSAT formula sheet that I created for my students. And in case you have missed the lecture, you can just always visit my DSAT special formula sheet. That would help you guys to find out the answers for all those hardest questions. If you're targeting 750 above, beyond 750, or a perfect score, these theorems are going to help you a lot for all those question number 18, 19, 20, 21, 22 module 2 questions. Thank you.